Hello and welcome again to our channel Bitastro. Suraj here, and today we are going to do the second part on the Lagrangian mechanics sections, and in this video we are going to discuss about the principle of the virtual work and quick recap of what we have studied in our previous video and what the exactly the problem that is constraint creating and how to solve the problem of the constraints that is creating the Lagrangian mechanics. Okay, and finally some problems that is used to solve the NLM problems using the principle of virtual work, so that you can have a crystal clear idea of why generally we assume that there is a virtual displacement, what is a necessity. So you will understand that this is a necessary because it can use to solve different types of the mechanics problem in a very good way. So let's start our today's video on the Lagrangian mechanics sections of the part 2. So in previous video we have studied about how the constraint is creating some of the problems. How? So let's see here. Suppose that I draw a circle here. Okay, तो मैंने यहाँ पे एक circle को draw किया. Okay, or when we govern that suppose that particle is there. Okay, some particle is here and the coordinate position of particle at this particular point is, let's say, x and y. We can write yes, and suppose that radius is r. We can denote this as a vector form also, that r is equals to the x I cap generally and plus y j cap, and you understand this all things. Okay, what happens is that you will see that particles is restricted to move only in the radius of the circle and it cannot move outward like this. It has a fixed distance from the center, which is the radius r. It means there is a constraint in this equation, and in this equation there is a constraint. And what happened is that now x and y are dependent upon each other. How? Let's see. How can we find the magnitude of r? Magnitude of r square is equals to the x square plus y square. Okay, so this is a thing of finding the magnitudes. And what you see that, yeah, x and y are dependent upon each other. So this is how there is a use of the generalized coordinate scheme. So यहाँ पे ये हो रहा है कि x और y जो है वो दोनों एक दूसरे पर डिपेंडेंट है. इट मीन्स कि ये प्रॉब्लम है कि अगर ये दोनों एक दूसरे पर डिपेंडेंट है तो एक जनरल इक्वेशन को बनाना डिफिकल्ट है. इसलिए हमने लैग्रेंजियन मैकेनिक्स में एक नए कोऑर्डिनेट्स का इन्वेंशन किया, एक नए कोऑर्डिनेट्स इन्वेंट किए, व्हिच इज व्हाट वी कॉल द जनरलाइज्ड कोऑर्डिनेट, which is independent of everything and capable of problem of solving all of the problems related to the particular particle and can govern that whether the particle is going to be. So that's why Lagrangian mechanics generalized coordinate has a very weightage, and here x and y are not the generalized coordinate because they're dependent upon each other. That's why we introduce the concept of generalized coordinate, and the generalized coordinate in the circle is what called the theta. Let's see, let's draw a big circle to understand this. So हमने यहाँ पे एक circle को draw किया. What we found is that this theta, okay, this theta is alone capable of doing all of that what where the particle is going exactly to be, and it is independent of also x and y. That's why we choose generalized coordinate theta in this circular motion. Now you understand the importance. Now you understand what the constraints are doing. We don't want any type of the relation between the two coordinates. We want very simple things. So what we choose is that we choose a special type of coordinate called the generalized coordinate, which are independent upon each other, and that's the criteria for the generalized coordinate. And that's how we solve our problem of constraints. What happens is that suppose there is a constraint, x and y are dependent upon each other, so we can't make an equation, that can govern this. It will become very complex. What happens is that let's choose another generalized coordinate. x y को एक्सप्रेस करके हम लोग एक नया कोऑर्डिनेट को चूज करते हैं, which is our theta, which is independent of the constraints also, and it can also govern this particular particle motion in a very good way. That's why there is a necessity of the generalized coordinates in the circular in the Lagrangian mechanics, and that's why it's a very types of the weightage also. I hope that understand what the quick recap of my previous video, that what's the problem constraint are creating, how to solve the problem. So the problem of constraint is solved by introducing the introducing the new coordinate called a generalized coordinates. Generalized coordinate can be anything. If x and y are not dependent, they are also called the generalized coordinate, but in this condition they are dependent. That's why they are not called the generalized coordinate. And that's the quick recap of what we studied in the previous section. Now let's move toward the general equation. And one more thing important in the generalized coordinate is the relation between the generalized coordinate and the Cartesian coordinate. How we can find the relation? Suppose that how we denote, first of all, generalized coordinate. We denote generalized coordinate in this sign, like q1, q2, q3 till qn. Okay, so this is a representation of our generalized coordinate. And what is the relation between the generalized coordinate and this particular this particular Cartesian coordinates? What is generally the relationship between? We also know that there's a relationship between the polar coordinates and the Cartesian coordinates. फिर ये generalized और ये Cartesian में क्या हमारा हम लोग कैसे लिख सकते हैं Cartesian coordinates से और इनके बीच में relations को? So we can write this in a very good way, and that is this. So the representation between this is very important, that xi is equals to the xi q1, q2, q3 till qn. How we have derived that r is a function of our generalized coordinate, and this is the representation of our Cartesian coordinate in x. In y, you can similarly do this. In y, we have to substitute this as yi, and then again here q1, q2, q3, and whatever this is. So we have represented the Cartesian coordinate in terms of our generalized coordinates. And the Cartesian coordinates are the functions of the generalized coordinate, as you can see here. So this is a bit more important topic that is important and came in the exams. And this is also very important while deriving the Euler-Lagrange and the Lagrange equation generally, which we will discuss in the next video. Okay, now move to our next topic. We studied what the generalized coordinate, what the importance of the generalized coordinate, because it just removes the problem of the constraints. You do not have to worry about that, what the constraints in the thing are. You don't have to worry. Just pick the generalized coordinate, use the principle of virtual work or the Euler-Lagrange equation, and extract what you want. Okay, so now let's move towards our next thing, which is the principle of virtual work. And this is the first general equation that is coming in the Lagrangian mechanics. So principle of virtual work. Suppose that name is the virtual work. You will see that it is bit more very uneasy for you to imagine, but in physics, assuming something will reduce complexities in a great way, and one of the good example is the principle of the virtual work. What it says, so let's see what the principle of virtual work is exactly saying. Okay, principle of virtual work says, I will not go directly to the definition. First of all, understand it. Suppose that the force is zero, the equilibrium, all of the net forces is equals to the zero, and this is the conditions for the equilibrium, that all the summation of I is equals to the zero. All of the forces summation to zero. Okay, what we do in the virtual work is that we add a arbitrary displacement. Called del Ri. This is not the exact displacement. It is called the virtual displacement. It is called the virtual. It do not generally occurs, but we just assume that there is a virtual displacement occurs even there is an equilibrium system. So this is the virtual displacement. And what we said is that if summation of Fi is equals to 0, then summation of Fi into del Ri is equals to the 0. And this is called the principle of the virtual work. So let's principle of virtual work क्या कहता है? अगर हमारा equilibrium system है, यानी all of the net forces are 0, then the work done, you can say that this is work done, remember this is work done, force into displacement. Okay, then the work done by the force and when there is a virtual displacement is also equals to the 0, because Fi is equals to the 0, and this quantity is also 0. And this is the principle of virtual work. This is the principle of the virtual work. It says that, easy language, ये कहता है प्रिंसिपल ऑफ वर्चुअल वर्क कि अगर हमारा नेट फोर्स 0 है, तो जो वर्क डन होगा हमारे ये फोर्सेस के द्वारा, दिस फोर्स इज नॉट वर्चुअल, दिस इज द रियल फोर्स दैट वी अप्लाइड. सो द नेट फोर्स and a virtual displacement work done is equals to the 0. Its dot product is equals to the 0. And this is called the principle of the virtual work. Why this is virtual? Because you see that here is a virtual displacement. Here is a virtual displacement. That's why we call this is a virtual work. But in exact situation, there is no any type of the virtual displacement occur. We just assume it occurs. And that's why its name is virtual. And it is called the principle of virtual work. I hope that you understand that what exactly this says, principle of the virtual work. It says that suppose that कि हमारा एक system, let's imagine a system, okay? Let's imagine a system here. Here we apply some force F1 and here we apply some force F2, okay? F1 and F2. And we have to find out that what should be the magnitude of what should be the ratio of F2 by F1 so that the system remains in the equilibrium. So that the system remains in equilibrium, and you know that it is obvious that it is the ratio is equals to 1 by 1. This ratio is to be 1. Then there will be a net zero force. But what we solve it using the principle of virtual work, that we assume that there is a work. Let's imagine there is a work, because if you imagine that there is a work and if you do the calculations, it will exactly give the same result that you do with the Newtonian's perspective. तो हमको लगता है कि अब आप एग्जांपल्स के थ्रू हम इसको और अच्छे से समझेंगे कि हमने तो एक डेफिनेशन देखा प्रिंसिपल ऑफ वर्चुअल वर्क का कि वी इमेजिन, बट रिमेंबर हियर Fi, okay, so here Fi can we also break down here Fi is the net force, and we can break down Fi in the two things. Let's denote is Fia. I'm just denoting it as a Fia, okay, so don't confuse this. This is Fi, which is total force. So Fia can be written as Fi plus small fi. Okay, here we break down our forces into two forces. So this is the applied force and this is the force that is the constraint force. You can imagine that there's a 2 or 3 particles. So if you apply the force to first particle, the force will apply also to the second particle. So the force that applied to the second particle is called the force of constraint. So can we write down Fia as Fi plus small fi, where small fi is the force of constraint. Okay, so now breaking down this, we can let that summation of Fi. Here this Fi is the applied force, Fi del Ri, sorry, here Fi del Ri, and plus summation of small fi dot del Ri is equals to the 0. We break down this into these components. Okay, now next step what we can do is the work done by the virtual work, which is this, the work done by the constraint force here is equals to the 0, is equals to the 0. This particular force of constraint work, because in general cases the force of constraint and the dot product of the displacement is equals to the 0. Because suppose that I imagine a situation here that there is a box here and it is lying on a surface. Okay, so we say that normal reaction is the constraint force, and here in this direction, if there is a del Ri, then you see that here is a 90-degree angle between them, and such that their dot product is equals to the 0 and work done is equals to the 0. But remember, all the time this is not equal to the 0. All the time is not equals to the 0, and the force of constraint is normal reaction. The force of constraint is the normal reaction which is restricting the particle from moving downward. Moving downward, that's why it's called normal reaction is the constraint force, and this summation is equals to 0, and what we left is that summation of Fi. Remember, this Fi is the applied force, don't confuse with this. So let's say this is F dash I, okay, not to confuse, F dash, okay, del Ri is equals to the 0. It means applied force. Now you see that this is the applied force. So applied force dot product of the virtual displacement is equal to the 0, and that is called the principle of the virtual work. That the work done were virtual, or you can say that when you apply a force on a system such that all the forces summation is equals to the 0, such that all the summation forces is equals to the 0, the work done when there is a virtual displacement is equals to the 0. Okay, the work done by the force if there is any virtual displacement is equals to the 0, and it is obvious because Fi is equals to the 0. And this is very important principle that you have to remember. But you can't understand just by remembering that, okay, what virtual work is. Doing some of the examples can really feel you like that what this is the virtual work is. You will find that, oh, this is virtual work, this is how interesting is, and how you can solve the complex problem using just this principle of virtual work. So let's take an easy example first of all to understand this. So I'm taking an Okay, so let's take a very famous problem in Newton's laws of motion, which can solve by Newtonian mechanics also, but I will prefer to solve it with a Lagrangian, because if you solve a single problem from different methods, then you are gaining some new concepts also. Okay, so let's say this is theta angle here, and I attached a wedge from which a pulley is attached and it is fixed. Okay, remember this is fixed, and suppose that here I have attached a block which is mass 2. Okay, and here we have another block as mass let's say this has mass 1. Okay, so what you have to find out, this is a very good example. You have to find out that prove that the system is in equilibrium. Prove that the system is in equilibrium if I think sine theta is equals to the m2 divided by m1. अगर ये सिस्टम इक्विलिब्रियम में है तो प्रूफ करो कि अगर साइन थीटा m2 अपॉन m1 होगा तभी ये सिस्टम इक्विलिब्रियम में होगा यूजिंग द प्रिंसिपल ऑफ वर्चुअल वर्क. हमने जो अभी ये वाला डेफिनेशन पढ़ा, इसकी मदद से हमको इस वाले इक्वेशंस को सॉल्व करना है. कैसे करेंगे, चलिए शुरू करते हैं कुछ बेसिक न्यूटोनियन मैकेनिक्स के आइडियाज को लेके. सो इसका आंसर, ओके, हाउ वी कैन सॉल्व दिस क्वेश्चन. सो लेट्स सी. Suppose write out the general equation. Applied force F, the force that is acting on it, F I del Ri is equals to the 0. There are two forces that way summation is 2. You can write it as F1, sorry, F1 into del R1 plus F2 into del R2 is equals to the 0. Okay, simple. Now elaborating it, what we can find. F1 force, what type of force is acting here? So here is acting downward force, which is the m2g. And you know that while solving in the Newtonian's perspective, you have to also take the tension force, which is the constant force here. But using the virtual work, we have just removed after the from constraint here. हमने कंस्टेंट को ऐसे रिमूव कर दिया, हटा दिया. देखिए कि इतने इजी इक्वेशंस हो गए हैं. हमने जब कंस्टेंट फोर्सेस को हटा दिया है, हमें सिर्फ उसी फोर्स से मतलब है जब जो इस पे लग रहा है नीचे की तरफ. नो एनी टाइप ऑफ द कंस्टेंट फोर्स इज रिक्वायर्ड. सो लेट्स सी हियर व्हाट वी कैन डू. ओके, नाउ सब्स्टिट्यूटिंग हियर m2g into the del Ri into the del R1 plus here the force is acting downward, and you know that what is this? This is equals to the mg sine m1g sine theta. m1g sine theta. Okay, so you can write it as m1g sine theta. m1g sine theta is equals to the 0, del R2. Oh, sorry, here's a mistake. Here is 2. Okay, here is 2, and there is R. Sorry guys, there is a mistake here in the subscript. There is a mistake. Okay, let me correct it. F1 force. Okay, let me correct it. Subscript में mistake आने से हो सकती है प्रॉब्लम, इसलिए ये प्रॉब्लम. Okay, now F1 force. Let's say the F1 force is the force F1 force is this. F1 force is this, and this is the F2 force. This is the downwards F2 force, let's say, and this is the F1 force. Okay, now let's solve F1 del Ri plus. Okay, F1 we can write it as M1 G sine theta. Know why sine theta? You can draw the FBD. You can draw the FBD such that drawing FBD, what we found is that this is the mass of the block. Here you can find it is the mg force acting. Here is the mg force. Sorry, here is the mg force acting, and this particular, and here this particular angle is theta degree, and you know that where is a theta, there is an mg cos theta, and just perpendicular to it, which is downward, there is mg sine theta, what I have written here. Okay, this is mg sine theta and what I have written here. Okay, so mg m1 g sine theta del r1 plus f2. What is f2? The f2 is the only m2 g del r2 0 is equals to the 0. Now g and g will cancel out, because if you common g and take it to the another side, this will cancel. What you left is m1 sine theta del r1 plus m2 del r2 is equals to the 0. Now listen carefully. Suppose that, let's move that this block, this A block, suppose that this is A block and this is B block. Suppose that this A blocks move in the certain direction del Ri, move in a certain direction del R or del R1. So you know that if it's move in a del R1 direction, then this particular mass will up del R2, it will take del R2 displacement, such that del R1 is just the negative, is equals to the, this is very important conclusion. Let me understand it. देखो, अगर हम इमेजिन करें कि ये A ब्लॉक नीचे जा रहा है, del R1 एक डिस्प्लेसमेंट कर रहा है, तो ये स्ट्रिंग सेम है, तो जितना स्ट्रिंग खींचेगा del R1 उतना ही ये ऊपर जाएगा del R2, और ये दोनों अपोजिट डायरेक्शन में हो रहे हैं, इसलिए del R1 is equals to the negative of the del R2, is the negative of the del R2, because it is in the downward direction and here the displacement is the upward direction, and they are equal and opposite direction. Okay, this is very important. Okay, this is very important. Okay, now if I just do simplify here and applying this particular result that we obtained, what we'll found is that here m1 sine theta and negative of the m2, sorry, here I have forget about the del R2, del R1, sorry, no worry, minus m2 del R1, because here this is equal and opposite, and putting the value of del R2 as negative of the del R1, and take it to the another side, m1 sine theta del R1 is equals to the m2 del R1, such that this del R1 and del R1 will cut out, and the equilibrium condition is that the sine theta should be m2 by m1, and here is no any type of the tension force that I have taken, and that's the beauty of the Lagrangian mechanics, because it just removes the complexities of any type of the constraint force, maybe it's tension and another force, and what you have to work is just purely applied force. And this is the answer of our question. I hope that you understand it very clearly, that how using the principle of virtual work we can arrive a situation. We can also solve it with the Newtonian's perspective, and in the Newtonian's perspective it is also very easy, but you have to solve this in another method. So Lagrangian mechanics is also a very better way to solve this. I hope that you understand this all, that what exactly the principle of virtual work is and how to do the principle of virtual work to understand this. So this is our today's video where I've studied about the principle of virtual work. You can't do any time. मेरा पर्सपेक्टिव ये है कि आपने वर्चुअल वर्क को पढ़ा तो उसको समझने के लिए आपको एग्जांपल्स की जरूरत पड़ेगी, क्योंकि फर्स्ट ऑफ ऑल व्हेन आई स्टडी आल्सो आई फाउंड इट दैट why we have to assume that there is a virtual displacement, but when you see that it's great uses, then you can conclude that yes, after assuming that there may be a displacement, this is a very easy thing and you can easily derive and solve various types of the problem in physics. That's why I prefer you to learn the Lagrangian mechanics. So this is my today's video on the Lagrangian mechanics, and hope that you like. And in the next video, we are going to discuss some other applications and advanced applications of the Lagrangian mechanics. And finally, the Lagrange equation. And after this, the velocity dependent potentials and all that things. So this is my today's video on the Lagrangian mechanics section. Hope that you understand this. So thank you for watching my video.